First, I'd like to thank Juan very much for the invitation. So today, so the talk, this is about a few directions that I'm working on, and that's directly inspired by the previous works you heard. You have seen the list of a lot of papers. I'm not going to list all of them. These are the two earliest ones about these new ways to understand the evaporating black hole in holographic duality. So although I'm going to talk about some toy models, some of them are more directly related to the SYK part, maybe more directly related to these works. But the tensor network, we would like to study some different features of similar models with scrambling and coupling to the bus, competing with each other, interplay with each other. So these works involves discussions with many people. Start with a discussion with Masamichi and Zhenbin and Ignacio Sirac and Lorenzo in Ignacio's group, and my colleague Vedika Kamani, and also Shun Yao and Xiaoliang in my group. And then the later part, if I have time, I'm going to talk about the some SYK model work that's mainly the work of Yiming Chen and Pengfei Zhang and Shun Yao. Oh, I forgot to put my name here. Okay, so the tensor network models, so we want to think of some models that describes chaotic dynamics but coupled to the bus. As we already know very well, we can use some tensor networks to describe like Brownian circuits that are with or without spatial locality that can describe chaotic dynamics that has some similarities to black holes. So we studied several different kinds of tensor networks, but here I'm going to talk about one that has a particular nice properties that's based on this very nice work of Nima and Douglas and collaborators. And so that's about this fast scrambling conjecture, that paper they have. And so this is just the k-local gates. So you randomly apply, in this picture, bilocal gates to n qubits. So you have n qubits with dimension d, and then you every time you randomly apply some 2-qubit gates, and then this is an ensemble. So it's Brownian, means the gates are independent from each other. And then so that's the original model, and then the modification is now you can consider some coupling to the bus, and the coupling to the bus could be some whatever simple things. And for example, I could consider that the bus is controlling a Pauli operator that's applied to the system, and with a probability epsilon. So with a large probability, I'm not doing anything, but with a small probability, I'm applying a Pauli. And I can consider these bus qubits to be just free flying. It means every time there's a new qubit coming in to interact with my system, that will make this calculation particularly easy. Okay, so this is the setup, and then so you know that these kind of bilocal gates, it describes like a system where a single operator is going to become bigger in the time scale of log n. So it has these kind of scrambling properties. And then so the nice thing, very nice thing of this model is it has permutation symmetry between the different qubits once you average over the different choice of random gates. So that simplifies the calculation a lot. And when you study the purity of subsystem, so like the trace of rho square, so as you see, that's always the thing that we know how to calculate. And then so you can take a subsystem and calculate the purity. Generically, it's a property of a subsystem, but if you have permutation symmetry, then it's only a function of the size of subsystem. So so if you have n qubits, you have n+1 numbers. Just well, the empty set always have p equals to 1. So so you're going to have n numbers that are non-trivial. So this is the purity of the system. And then so now you can take another limit to simplify the problem, which is take continuum limit in time. So it's like going to a stochastic differential equation. Like you average over the time evolution. So instead of like like random two-qubit unitaries, you consider applying a random two-qubit Hermitian for a short time, and then switch to a totally different random two-qubit Hermitian. But in the middle, in between of them, you insert a coupling to the bus. And then you take the continuum limit after you take 2 copies to calculate the purity and average over the randomness, you get a nice differential equation for the purity. So like if you know the purity of subsystems of general size for the earlier time, that determines the next time slice. Because the Brownian thing, because the fact that every step is Brownian erased all the history memory. So this first line was already in the paper of Nima et al. About the fast scrambling case. That's the dynamics of the system itself. So let's look at that first. So you have this purity of any regime with size n. The time evolution of that depends on the purity of regimes with smaller and bigger size, and there is a constant term here. And the property of this differential equation is it has 2 solutions that are static in time. One is exponential decaying, one is exponential growing. And the exponential decaying solution just means the maximally mixed state. Means because the purity will be exponential of the entropy, of minus the entropy, right? So it decays exponentially. And if you take the superposition of the exponential decay and exponential growing solution, that's the random pure state. So there are these 2 fixed points. Like if you have a system which is pure without the coupling to the bus, of course it stays pure. So you will get a purity that looks like the left side. This is the log of the this is the minus log of the purity, which is the second linear entropy. And you see that if you start from a pure state with 0 entropy, so this is as a function of subsystem size. You see it grows, and in long time it approaches this behavior of a random pure state. Now with bus, you add a new term to this equation. The new term is very simple. It's just like a first derivative of this purity. Then that term select one of the 2 fixed points. Now you only have one stable solution in long time, which is the maximally mixed state. So in the end, the system is going to couple to the bus and get equilibrium with the bus. So you see, like if I turn on a small coupling just to separate the 2 time scales, you see when the coupling is very small, in short time, I first scrambles and go to a entropy that's very similar to the pure state behavior. But then in long time, the entropy of the whole system will increase until it becomes maximum. So this tells me, like this simple differential equation tells me this interplay between these 2 different processes. You can see that more clearly in this time dependence. So the red line is the entropy of the whole system. So that's the Page curve, like the entropy grows and saturates. And now the calculations are all finite n, so it's a crossover. So the entropy linear grows and saturates. If you look at the entropy of a subsystem that's smaller than half, like here, a subsystem that's smaller than half will just thermalize due to the coupling with the complement system, even if you don't have the bus, and then it will just stay there at the maximal value, right? But the subsystem bigger than half we'll see 2 different time scales. It first, due to scrambling of the system itself, it will reach an entropy that's like volume law for the complement. And then in a longer time, it's going to evaporate, and the entropy becomes the maximal possible value, proportional to its own size. So that's how you see, like there are 2 different time scales in the system. That the evaporation, the Page time, and the scrambling time. So then you could study many other properties of the system, such as if I put in a message into the black hole, then ask where it goes. Right? So I can put in 1 qubit, and then 1 qubit of quantum information, and then see and calculate some mutual information quantities. Again, ideally, we want to calculate the von Neumann mutual information, but now we only know how to calculate the Rényi version. So if you calculate the mutual information with either part of your system or the radiation, then you know where is that message. Right? So at early time, the message is going to be in the black hole. So the mutual information with the black hole is big. And then after the page time, the message will go to the radiation if you put in the message earlier. If you put in the message later, it takes a scrambling time. It goes to the radiation. So these you can apply the same differential equation. You just need to change the initial condition because the Brownian circuit is the same. So you could study this by just running this differential equation with different initial conditions, and you see that this is what happens for the mutual information, the Rayleigh 2 mutual information of your message. Oh, I forgot to explain that this line means that I purify my qubit by another qubit. I have an EPR pair and put in one qubit into the system, so that now I have an ancilla qubit A entangled with my system and bus. So that allows me to study mutual information of the ancilla with either of these parts. So now if I look at IAB, which is the mutual information with the bus, then you see it's if I put in the message early, it stays in the black hole until page time and then quickly goes out. If you look at the mutual information with a subsystem of the black hole, you see that it actually first grows and then at page time it goes out. And that growth is because at the initial time, only one site knows the information. The rest doesn't know anything. And when you in a short time of basically in a scrambling time, this message goes to many qubits, so that there's a lot of sites. Like if C is big, then there's a lot of C that you can extract that message. So if C is bigger than half, you see this increase. If C is smaller than half, you don't. So if C is bigger than half, you see this increase of mutual information, and then it goes to the bus after the page time. So you could also, so what I shown earlier here is when I put in the message at the initial time 0, when all other states are in the pure state. You could also do the more general case, like I start from a pure state, and then after some time later, what I call T in, I put in this qubit. So what I do is I introduce a swap gate. I have this EPR pair, and then I swap it with this qubit in the system. Sorry, there's some error here. So the system qubit goes out in this red line, and then this ancilla qubit goes in here. And in that case, you study the mutual information, and this plot is the mutual information with the radiation. So the yellow part is where the mutual information is almost maximum. So the maximal case, if you look at these two lines, let's say if I have qubits, the maximal mutual information will be 4 log 2, because there are 2 qubits involved. So the yellow one is like 4 log 2. So you see, like if I put in it early, I need to wait until the page time for it to go out. If I put it in late, the horizontal line is the time I put the perturbation in. So this is 0, because it's before you put it in. So if I put it in late, it takes like a scrambling time to go out. That's like checking the Hayden-Prescale result. And this line here, by the way, is saying that if you put in the initial state very early, so it's like going back here, then the maximum mutual information is actually smaller. It's like only 2 log 2, because this qubit goes out, but it's not entangled. So like the maximum mutual information you can get depends on your initial state. So that's why there is a slightly different line here. And I just want to make a little comment about the relation to the entanglement wedge discussions in the recent works. So we don't have this model is like we know it doesn't have a bulk dual. If I think of the analog with the system with holographic dual, then the tensor network is like describing the boundary dynamics. It's like living here. So there is we cannot talk about the entanglement wedge, like living in the bulk, but we can talk about like on the boundary at which time your message goes out your message is out of the entanglement wedge of your system, of your black hole, which means the message goes to the bus, right? Goes to the radiation. So if you plot the mutual information with the black hole, then it's basically just the opposite to the picture I just showed you. So the mutual information is like big here, and then after page time it becomes small. So I think that this line is roughly speaking is like what happened if you throw in a message earlier. So it takes some page time until you go out to the entanglement wedge of the bus. And then if you throw in the message after the page time, then it takes some constant time, some constant scrambling time for it to go to the entanglement wedge of the bus. I didn't mention that earlier, but this model is like the eternal case in this work of Ahmed and Raghu and Huan, because the bath and the black hole both are like in the infinite temperature, so we don't really have a finite temperature that we can tune. So that's also why like the black hole will not really evaporate; it will just equilibrate with the bath. You can also study other quantities like the 2-point functions. So a 2-point function and 4-point functions. So based on this previous work we did here, that we can relate the average the out-of-time order 4-point function to some Rényi 2 mutual information of this channel. Like if you take the doubled state of this quantum channel and calculate some mutual information, then the 2-point function will probe the mutual information between small regions and small regions, and the out-of-time order 4-point function at infinite temperature will probe this mutual information between small region and the big region. If your operator is in D, then it's probing mutual information with the complement, which is C. So you see like this kind of difference between the behavior of 2-point function and 4-point function. Like at early time, the deviation is accelerating rather than slowing down, and that's how the OTOC behaves. Okay, so basically this the bottom line is that this is a nice model that you can use to study many different quantum information quantities, and it allows you to do this computation very efficiently. And of course, it doesn't have this conserved energy. That's why like we couldn't use it to model the real like evaporating black hole, which in the end disappears at some finite time because there's no energy conservation. But there is a way that we could model energy conservation. We could have an analog of energy conservation in the tensor network models. So it's difficult to introduce energy conservation, but you could do a charge conservation instead. If you have a charge like U1 charge, and then the bus has a 0 charge, and the bus is infinite, then the charge is going to go away, and if your Hilbert space dimension goes down with charge, like charge 0 is like vacuum, then that's similar to the role of energy conservation in the black hole evaporation. Like when the energy goes down, entropy goes down, that's how the black hole in the end evaporates. Right? So you could consider like a similar model as I just said, except that the coupling between 2 qubits is preserving charge conservation. So like for qubits, you have 4 states, and you are only going to allow coupling between like charge 0, 1, 1, 0. So charge 0, 0 will not do anything, and charge 1, 1 will stay 1, 1, get a random phase. So yeah, so you can have a model, and it's much harder to study, although we can still have some simplification using the permutation symmetry. So here I'm just showing some simple like direct exact diagonalization for a small size. These calculations are done for 8 qubits. You could do a little bigger, but so you see like the entropy. The von Neumann entropy, well, in this case, because it's exact diagonalization, we could do both. Like von Neumann entropy and Rényi entropy, you see if I start from a pure state, then the coupling to the bus will make the entanglement entropy increase. But at some point, it's going to reach the maximal possible entropy for that given charge. And then the charge gradually leaks away to the bus, so the entropy is forced to go down. So basically, there is a page transition here. And you could also study these other properties, like I put in the message and how the message goes out. We studied that in some other version of these charged tensor networks, which I'm not going to show here. so basically, other than it evaporates in a long time, if you make the evaporation very slow, it's very similar to the previous model. Okay, so apparently, so as there is some so because the tensor networks are describing the dynamics on the boundary, we don't really know how to go to the bulk. I want to make a little speculation about how to think about the bulk. This is very preliminary, but I hope I'm allowed to mention some crazy ideas during this workshop. So we know there is an intuition that when you evolve this, let's say the eternal black hole, when you evolve the state above in time, this wormhole grows, and it's more or less like the length of the circuit is growing. Right? The length of the circuit that prepare that state is growing. So it's, roughly speaking, it's like this line is like the time direction of your circuit. But how do we make this into a framework that really describe this intuition? So it's just recently I feel like it's actually natural to do that, because we know like a general way to understand tensor network is what is called PEPs, projected entangled pair states, which means whatever tensor network you have, whether or not it's like describing a unitary gates or describing states, you can generally think of them as obtained by two-step procedure. First, you prepare some EPR pairs, which are these lines, and that's called state L. In general, it doesn't have to be just EPR pairs, but some simple states. And then an L lives on this Hilbert space of all these lines. So it's going to be a Hilbert space that's both boundary and bulk. And then there's a state V which is defined on a smaller Hilbert space, which is like bulk only. And this V knows all about these chaotic dynamics and all these non-trivial things. But it's just a product of the vertex states on every vertex. So when you project out V, just like you measure and then you post-select on one of the output of the measurements on every site, then what you are left with is the physical state per psi on the boundary. Right? So that's the general way you understand tensor network. So I just want to propose that maybe we can think about the bulk time evolution as like a pair of two systems. There is a time evolution of the V states and the L states. And at any time, at any Cauchy slice here, you could take a Cauchy slice in the bulk and then look at the state of V and state of L. And then the overlap will give me the state of the psi on the boundary. So that's just a proposal. And that has a big ambiguity, because if you multiply any arbitrary unitary to V, which is restricted to the bulk, and do the same to the conjugate of that, to the W dagger to L, then this overlap is preserved, right? That's actually, I think it's not a problem, it's actually a feature. Like it tells, and part of that gauge symmetry is actually this choice of Cauchy slice. And when you choose the Cauchy slice that ends on the same points, it corresponds to you have changed what you call the V states and what you call the L states, but the overlap stays the same. And then, so when we push this to the future, and when you and if you move the boundary points, if you look at the Cauchy slice with the boundary points moved, then these two unitary evolutions do not cancel each other anymore. So you are left with some non-trivial evolution on the boundary. And of course, this is, I mean, in general, we cannot make sure that this evolution on the boundary that's induced by this procedure is unitary. So I don't have a general way to show in which case it works, but at least there is some examples I'm going to show you that some very simple examples that seems to give me a unitary evolution on the boundary. But I want to mention that if you push this to the future, to a very late time, it seems to naturally reduce to the final state of the Horowitz-Maldacena proposal. That I want to say, like, if I take a very late time, then the state of V becomes like that final state of the black hole, which is introducing the chaotic mapping that takes the qubits in the bulk out of the black hole, takes the interior qubits and map them out. So that's what the final state gives you. Right? So I think this is like a generalization. It tells you that you could define that state at any other time. It's just when you push it to the singularity, it becomes that final state. And I feel like it's natural for tensor network, and it may be, it also looks very similar to what Ahmed talked about, this brain, which is like time-like. Like you could take a tensor network state and project one side out and then study the other side. This looks now, if I think about the singularity in this way, then it looks not too much different from I just project the final state. So I really only have a very, very naive example that seems to be demonstrating that that this is possible. So I'm just considering, so as I said, I want to consider a pair of systems, the systems of the vertex states V and the EPR pair, the link states L. So I'm just considering an example where both are just having the trivial swap dynamics, like the qubits are moving and they are freely moving, they don't interact with each other. But there is some boundary condition. When they hit the boundary, they reflect it. And the V has two states. The red and blue corresponds to a vertex states that corresponds to the unitary gaze or the U inverse. So like the red is U, let's say the red is U inverse and the blue is U. And then the L is really just EPR pair, and after you do the swap, it's the same EPR pair. So the state of L basically just prepare all these resources of entanglement, and that doesn't do any other thing. But I cook up this boundary condition so that like the red becomes blue once it got reflected. And the reason why I do that is if you take a cut like this, like in the middle, like this is the dashed line here. If you take a cut in the middle, you'll see the red and blue cancel each other. So like the left and right side will be just simply entangled with EPR pairs because the U and U inverse cancel each other. But when you evolve up in time, you get more blues than red. And then so that's how your quantum circuit gets longer. So this is really just artificially designing a model where the V states are, the job of the V state is to print the circuit in space. And then the L is just preparing the EPR pairs. So this is really like a measurement-based quantum computation. Like you prepare the cube, you prepare the circuits, you do the computation in space rather than time by doing measurements. And then you can also consider coupling to the bath. And I want to think that as like modifying maybe the gaze a little bit. Like instead of U, you modify it a little bit. But if you have a large bound dimension for these bulk qubits, if you have a large bound dimension for these qubits, then you only modify a small dimension of that. Then it will have a small effect, and that's the important feature. That so if you have a small modifications, although these points are like time-like separated, when you move them here, it's actually still time-like separated because it's just a circuit along this line. But if these perturbations are having a small dimension, you can prove that they looks like independent degrees of freedom because of these error correction properties. And that's I want to say that's why this direction looks like space-like dimension. Did I miss the? 5 minutes. Oh, okay. Yeah. Thanks. Okay. So there is apparently a lot of things that we still don't know how to think of in this way. Well, we need a finite temperature in order to distinguish, in order to have a difference between outside and inside, and we need some calculation to show that this violation of quantum mechanics due to final state is small enough, and also the relation to the other thing Xiaoliang and I did about the space-time tensor network. It's not clear how to relate these two ways now. But at least I hope to say there seems to be a consistent way to have this spatial, to put this spatial holographic tensor networks in space-time using this approach. Okay, so in the last 4 minutes, 3 minutes, 4 minutes, I want to quickly mention the other kind of toy model that Pengfei and Yiming and Shunyu studied. It's mainly Pengfei and Yiming's work. I thought the previous 2 talks will talk about this a lot, so I don't have any introduction about this about this SYK calculation. So this is basically a follow-up work of this recent work that you just heard about, the Geoff and Douglas and Steve and Zhenbin. So they studied this SYK coupled to a SYK bus, which they didn't talk about. So we studied a slightly different problem where you have an SYK model coupled to a free fermion bus. It's just because I feel like it's more natural, and I like to imagine that there is a wave packet that could come in and goes out, runs in space. So I like this free fermion as a bus. And then you have a bilinear coupling, and this model has n SYK fermions and n free fermions as bus. So it's like a case where the bus has a central charge that's order n. And then you can solve these self-consistent equations in the same way as the SYK bus. And then this is just a diagram which shows that. So we have this eternal case, which means we have the black hole and the bus. The bus is blue and the black hole is black. And then so we have this thermal field double. So it's like thermal field double state evolved in time. This is what it means. And this is like cat and bra. So this diagram means I traced over the bus. So this is the density matrix of the black hole. And then you draw another copy and then think about this connected with that. That's like a trace of rho square for the black hole. So this is calculating the purity of the black hole. Okay, so you do these kind of calculations, and then similar to this calculation you heard from Douglas' talk and Geoff's talk, you find this transition between short time and long time, and the difference is that in short time, the Green's function is mainly diagonal, which means it's mainly like between like T2 and T3. That's what we call diagonal here, because they are directly connected. And this one is not really connected to that. So like T1 and T2 is like this block is very small, but it's not zero because we have a bilinear coupling. It's not zero. But when you have long time, then you see that this new point, the T1 T2 correlation becomes big. Like they just go through the bus couples them, and the effect of the bus become big in long time. So you get this first order phase transition. So the second Rayleigh entropy will grow, and then when the V is very small, there is a phase transition. And when V is big, actually it goes away. The phase transition goes away, becomes a crossover. So there is this first order transition, and then in the long time phase, it's basically just already thermalized, and the system and the thermal double of the black hole has like twice the thermal entropy. Not exactly twice the thermal entropy, like the entropy of what you should have in the thermal system of the entire coupled system. So one thing that a little different from what they did was we studied this overlap. So we want to like throw in a message and then see how much I can learn about that message in the radiation. So that's similar to that mutual information calculation I discussed earlier. Here, let's do a message that's just a single fermion. So I have this thermal double state at time t, compare with a perturbed state where you did a perturbation at earlier time delta t. So you can do a perturbation at delta t, and then you get rho r1. If you don't do any perturbation, you get rho r0. So you expect that like if this overlap is very big, that means that the two states are not distinguishable in radiation. For example, that will be what happened in early time. At later time, after page time, this overlap will become much smaller, which means that the information goes to the bus. So you can actually, just to make it more precise, what is the physical meaning of that quantity, we can think of this as a classical mutual information. You can think there is a classical bit which controls whether you do the perturbation or not. That means that you get a density metric that's just a classical sum of the rho r0 and rho r1 with the classical bit. And then you can ask what is the classical mutual information if you trace over the black hole. And that's determined by this overlap quantity. So this whole thing, the second Rayleigh mutual information, of A with R that you can calculate. So it's similar to what I showed earlier for tensor networks. And you see that mutual information jumps at the transition, becomes close to maximum. And there is also some increase before the page transition, which means because I'm applying a fermion here in SYK, so there is a chance that this fermion will, I mean, if you think the dual model is like a free fermion here and here, then there is a chance this thing goes out directly because there is a coupling. Right? So the message may have a finite chance of leaking out, and that's why there is already an increase here. But there is a jump here, which I would say the jump part is like what is the message that's going out in the form of many body operators rather than just the simple single body operator. Okay, so that's all. In summary, we have these toy models, and so there is apparently a lot of open questions. It would be nice to have a general framework, like in computing the bulk quantities and operators in the interior, and think about what's the implication to the black hole information paradox. Okay, thank you.